Hello everyone, welcome to the session 11 of this AI engineering course. So if you have followed me along, you have seen in the first 6 sessions, we have built AI agent from scratch with raw API calls, with no agentic framework and every step clearly visible. In the session 7, we rebuilt that agent using OpenAI SDK and you have appreciated how much manual plumbing it has removed. Then in the next sessions, we have created multi-agent system using handoffs with guardrails and tripwires providing safety layer around that agent. Then in the last session, in session 10, we took the turn. We covered the foundation of RAG, which is one of the most important and critical topic of AI world today. In this session, we will go a little bit deeper. We will cover similarity search, which is the raw engine behind the RAG retrieval, and we will also cover the various kind of vector DBs which power the modern days RAG applications. So without delay, let's get started. So for today's agenda, we will start with recall and precision, an important concept which will give you vocabulary to evaluate and tune any RAG pipeline, including the advanced ones, which we are going to cover in future session. Then we will move into our main topics. We will cover similarity search and different search strategies like KNN and ANN and different type of vector DBs. Finally, we will end it with hands-on on ChromaDB so that you can see it all working in practice. Now let's start with recall and precision, the retrieval trade-off. Let's understand these both terms recall and precision with the help of an example. Let's suppose you have a vector database in which you have stored 100 documents by dividing into chunks. The chunk size is 500. Let's say user firing a query about the laptop and the actual relevant chunks in the system based on the user query is 10. But let's suppose say you are retrieving only 8 chunks. This is because you have defined a factor called k as 8. Now k can be any value. You can retrieve one chunk, you can retrieve 5, 8, 10, 20 depending on how you configure it in your RAG system. Now you can get it. You are not retrieving all the relevant chunks because all relevant chunks in the system is 10 and you are retrieving only 8. So immediately a question comes to your mind, why not increase it to 10? We will come to that in a moment. Now, out of 8 chunks which are retrieved, keep in mind it is not necessary all are relevant. It could be like 4 of them are relevant and you are retrieving other 4 which are irrelevant. So these numbers actually help us to get two ratios, recall and precision. Now recall is number of retrieved chunks that are relevant upon actual relevant. So relevant retrieved upon total relevant is raw recall, retrieving around 40% of your actual relevant documents. And precision is how many of the retrieved chunks are actually relevant, which is 4 by 8. So I know like it is little tricky to understand in first go, but I will suggest you to go through this lecture again so that you can firmly get this idea. Now coming to back to our question, which we have asked earlier, why not just increase this k factor to 10 here so that we are actually sure we are at least retrieving all the relevant documents. So that I have covered is here. We have increased the k factor to 10 here. But what happens in for some other query, the number of relevant chunks in the system are only 2. Suppose a user is asking about what is RAG. You may not expect like there are many chunks which are storing the information of what is RAG. It may be present in 1 or 2 chunks. Suppose say you have increased the retrieve chunks to 10, then it means you are retrieving so much noise from the system also. So retrieve chunks that are relevant, let's say you are retrieving all the relevant chunks, whatever they are present in the system, you are retrieving 2. So your recall factor here is 2 by 2, which is 1. You are recalling 100% of the relevant chunks, but precision dropped considerably. So now you have retrieved 10 chunks, but out of those only 2 are relevant. Think how much unnecessary irrelevant information you are sending to LLM as a part of your RAG query. No wonder the result will not be that much optimal. This is why recall and precision are some of the most important considerations to keep in mind while designing your RAG pipeline. This is why we have covered in the beginning, so that whatever new topics, whatever new concept we will cover, you can keep asking in your head, is this helping in my recall? Is this helping to improve the precision? Keep these two ratio in your head as this will help you to design an optimal RAG architecture. So now let's move on to the similarity search. In similarity search, we find the vector closest to the query vector in high dimension space, which is not the exact match. We do the proximity search. So if you remember, we covered this topic in the previous session when we have covered the RAG architecture. So if you see this figure, you remember like there are some pre-processing steps. We first convert our raw data sources, our documents into embeddings. First convert them into chunking, then do the embeddings, store them into the vector database. At the query time, when user fires the query, it is also converted into embeddings called query vector. And then we find the vectors nearest to this query vector in the vector database and returns the relevant chunks of data, which is passed to the LLM. We returns the k nearest neighbors ranked by the closeness. Remember the k factor which we have covered just previously. So similarity search works for text, images, audio, anything you can or anything you want to embed. So now the question comes, what similarity search actually compares? So remember that we are comparing meaning. We are not comparing strings. We are not comparing the raw text strings. So the embedding model converts each sentence to vectors and we measure the angle between them. Remember there are three distance metrics. Again, this is something which we have covered in the last session. So cosine similarity, it measures the it measures the angle between the vectors and it is preferred for the text. So another thing is the distance, which is the magnitude of the vectors, and it is a geometric distance. Lower distance, which means more similar. And then the third is the dot product. So we use it when magnitude carries a signal. For example, popularity in recommendation. So let's revisit them once more, what we covered in the last session. So you remember, like, this is something which we have covered in the last session. So one is the Euclidean distance L2. It measures the physical distance. Cosine similarity, as we covered. Direction, most common in the RAG, and then the dot product, as it covers both the direction as well as the magnitude. So now let's do a small coding example in order to understand them better. So I have already created this example. There's nothing complex about it. So we created a small project in which we added our .env file, which has our open API key. Then I created a Python file, Similarity search, and let's go it from the top. So we first import NumPy package. If you don't know, NumPy is used for the scientific computation. Here we will use it for our vector maths, vector calculations. And OpenAI.env package, I think you are well versed with them because we have covered multiple times in the past. Then we load our .env file and then instantiating the OpenAI class. And then this is the function which we have defined. You pass any text to it, it will convert them into the vectors and returns the array of floating point numbers. Can you tell me how many numbers it will return? I think you guessed it right. It is 1536 numbers. The list of 1536 number it will return. And then we define the three functions: cosine similarity, L2 distance, and dot product. Cosine similarity, as you say, it is nothing, just the dot product divided by multiplication of length of vectors. So if these are normalized, like it is normalized here, so dot product and cosine similarity will come same. And then we have the L2 distance. L2 distance, there is a specific formula which returns the distance, and then the dot product we already covered. So then we define our query and then the list of documents in which this query needs to be searched to find the best matching text. And here you see, like, we call our embed functions, what we have written here, and convert all these text, the query as well as each of these documents into the vectors. And finally, we just have the print statements for formatting, and then we print each of these three scores, cosine, L2, distance, against the query vectors and print them. Right? And this is again just for formatting purpose. For example, here it is, we'll print our document text to the that will be left aligned and padded to the 45 characters. And here it is this number cosine, basically 8 numbers long. It is floating point number with 4 decimal spaces, and it will be right aligned. So in this way, we print all L2 as well as the dot also. So if the program is, let's just run the program. So the results are finally printed. So if you see, like, our query was, we are comparing the best language for machine learning against these three documents. And as you see, the first document was best match. Then deep learning frameworks and neural networks, less match. And history of ancient Roman architecture, like completely opposite. And we have got quite an expected result. The first document, it has the highest match. It is 0.5. Remember, like, cosine similarity is generally between 0 to 1. But sometimes it can be negative also when the meanings is completely opposite. As we see here, like history of Roman architecture, the values come in negative. That it means the vectors are in different direction. That angle between the vector is more than 90. You quickly see this diagram. If the angle between vector is less than 40 or less than 90 degree, then cosine value is positive. If it is cosine is 0, when the between vector is 90 degree, that means the text are unrelated, and it can be more than 90, it can be 150 degree when meaning between the vector is quite opposite, very much different from each other. So the same has the results we have achieved via our example also. So these three numbers, these three scores are clear to you. And one other thing to notice, cosine similarity and dot product are same because the vectors are normalized. If you see, we have normalized the vector during our calculation. But you will be then asking, cosine similarity is used for the text, but what purpose L2 distance and dot product is used? So let's quickly see that, although not important from that perspective, but let's quickly see. So where L2 distance is better in comparison to cosine similarity? So answer is the image similarity search. So for two images of cats having embeddings that are literally close together in space, closeness in all dimension matter, not just the angle. So for image similarity search, magnitude actually encodes the visual intensity and feature strength. So if the distance is less, then it means the feature strength is more matching. L2 respects that, but not the cosine similarity. So for image similarity search, L2 is better in comparison to cosine similarity. Similarly, where the dot product is better in comparison to cosine similarity, answer is the recommendation system. So let's take this small example. Suppose, say, a user listens to the hip hop music and his user preference is encoded into the vector format. This is a vector. So suppose the search algorithm, YouTube algorithm, has to match the corresponding strong songs which are matching to the user interest. So there is a one strong whose vector is this 8.5, 1.8, 0.9. It is quite popular and it has a million of views. So its vector is very much long. So, and then there's a niche hip hop track, not very much popular. It has the same direction. You see, it is 0.85, 0.18, 0.09. It is basically 10 times higher in magnitude, the popular songs, than this niche hip hop track. And if we compare the dot product, this is 8.5 that will come up and it is 0.814. This will be ranked, can be ranked higher by the search algorithm. This is why, in dot product, both the angle as well as the direction both matters. And that is why in such scenario, dot product is better. However, if we will do the, cosine similarity, you see here for both of the things, for both the songs, the number comes at 0.99, 0.99, and cosine, that's why I cannot tell them apart. So I hope like where to use L2, where to use dot product, where to use cosine similarity for RAG, all these things are now clear to you. A question again comes to my mind like, okay, we find the nearest vectors in the vector database using the similarity search, but how we find them? So there are two search strategies and we will cover them detail in the next session, but there are two search strategy. One is k nearest neighbors, another approximate nearest neighbor. In the k nearest neighbor, given a query vector, we find the k vectors with the smallest distance by scanning the entire data set. The key point is we scan the entire data set, so we get the exact and accurate results, but checks every time is performed against the each of the stored vector. So the problem here is the cost grows with every new vector added. We can find it can be find up to the 10,000 vectors, but painful beyond that. And similarly, there is an approximate nearest neighbor search strategy. It is very smart. It builds an index structure so that it skips most candidate and jump straight to the likely neighbors. So it trades a little bit of accuracy for massive speed gains. It is approximate but close enough for production. It is sublinear, fast even at hundreds of millions of vectors. So that is the search strategy because we have millions of vectors. So k nearest neighbor is hardly used. Mostly approximate nearest neighbor search strategy is adopted by every vector database. HNSW and IVF, which is inverted file index, are the two dominant ANN approximate nearest neighbor algorithm. We will discuss them in the next session 12. So now let's move on to our next topic, which is type of vector database. But before that, let's understand our motivation. Let's understand the difference between traditional databases versus vector databases. So first aspect is search approach. We know traditional databases, we search based on the exact match or keyword, or it is keyword based. So we use is equal to like or in operators to do our searching. While vector databases, we search based on the meaning. We cover that. Data representation, we have seen like in traditional databases, we have structured data. We store them in the row and column format. While in vector databases, we have multidimensional vectors encoding the unstructured data. Traditional databases does not understand the meaning, but vector databases we have seen they capture meaning via embedding models. Traditional databases does not handle or cannot handle synonyms, while vector databases words like increase, improves, and boost all carry the same meanings, and you can search based on that. Indexing, traditional databases use big trees for equality and range queries, while in vector databases, hierarchical navigable small word and IVF inverted file index are some of the algorithms which is used to perform nearest neighbor search. Scalability wise, in traditional databases, again, there are no hard and fast rule, there are various factors, but vertical scaling or adding more RAM or more CPU is something which we use to scale up the database. While for vector databases, we use horizontal scaling, meaning adding more machines. So that is what make it optimal to handle billions of vectors. Application wise, traditional databases are used for business apps and traditional and transactional system, while vector databases are used for RAG, semantic search, and recommendation system. So now let's move on to the type of vector databases. So there are predominantly four type of vector databases as we are seeing here, and understanding these categories help you to pick the right tool for the right job. There are more variations like graph vector database is also there, but these four cover the vast majority of what you will encounter in real RAG applications. So first is in-memory vector database. Faz and Now are the main example. They hold everything in the RAM, which make them extremely fast. The trade-off is there is no persistence. If your program stops, the data is gone. The second is disk-based or persistent vector databases. ChromaDB and LansDB sit here. So they write your vectors to local disk, so data survives between the runs. No server to set up, no cloud account is needed. You point them at folder and you're running. And they're ideal for prototype, local development, and smaller production workload. ChromaDB is something which we will cover later on in this session, and it is a great starting point for most RAG application. The third is the distributed and cloud native vector DBs, Viviet, Quadrant, Milvus, and Pinecone. These are some of the examples. They are purposefully built for scale. They run as a service and spread data across multiple nodes, support high availability and replication, and can handle billion of vectors. The last is hybrid vector database. This is important one to flag, even though we cover it properly in one of the later sessions. With sparse keyword search using an algorithm called BM25. The reason this matter is that pure semantic search has a blind spot. If users search for, let's say, exact product code or person name or technical term, practical vector search might miss it because meaning is not the distinguishing factor. The exact words are distinguishing factor here. Hybrid search gives you both semantic understanding and exact term matching. We come to cover this in depth when we will cover the hybrid rack in one of the later session. Now, another thing to note is your existing databases, like if you're running PostgreSQL or Elasticsearch or MongoDB, they also provide the vector database capability. So the embedding becomes just another column. If you see here, if the text is stored here, then your embeddings can be stored in another column, like it is seen here. A fixed length array of loads sits alongside your normal data. So it is good fit if you're already running PostgreSQL or Elasticsearch, vectors and relation data can be found in one query. It can scale up to even millions of vectors. So advantage is you have to operate only one DB, not the two. But you generally use dedicated vectors when you have billions of vectors and you need to perform hybrid search like using BM25 and all, which we just covered and we will see in one of the future session. And when the vector search is your primary workload, you don't need to work with traditional data. So now let's move on to the ChromaDB. It's an open source embedded vector database built specifically for AI application. And most importantly, its code is written in Rust, 3 to 5 times speed advantage over Python based alternatives. And it does more than just storing vectors. You get embedding storage, semantic vector search, full text keyword search, document search, metadata filtering, and even multimodal support for image and audio all in under one tool. And for integration, it works natively with LangChain and LlamaChain frameworks, OpenAI, Hugging Face, and it has official Python and JavaScript client also. And we will be using this integration directly in one of the future sessions where we will build a full rack chatbot using LangChain and ChromaDB together. So this is not just theory, you will see it wired up end to end very shortly. Deployment wise, there are two modes. Standalone runs client and server in the same process. That is what we will use for development and what you will see in the coding demo shortly. Client server mode runs a separate server via CLI or Docker for production use. And just quickly, you see like how the ChromaDB works. You obtain the embeddings. It is optional. You can convert the embeddings outside of ChromaDB also. Then you create the collection. You store the data. You then manage the collection using the update, delete, or rename operations. You can have a full CRUD on your data. ChromaDB treats this like a proper DB, not just a search index. And you then query. You pass the text or a vector in ChromaDB embeds the query and returns the k most similar documents ranked by the distance. Inside the engine, please note that it uses HNSW index internally for approximate neighbor search, and we will see it in the next session. Default distance matrix is L2 override to cosine or dot product per collection, and default embedding model is this one via sentence transformer. So now let's quickly move ahead and do a coding to understand how ChromaDB works internally under the hood. So I've already created a working example. The only requirement is you should install the ChromaDB package using the pip command. So we will be using the ChromaDB with the persistent client. That means everything we store gets saved to the disk and survives between the run. We will walk through three things in the order. First, storing the document with the metadata, then running a basic similarity search, and finally applying filters to narrow down what gets retrieved. So a point worth noting before starting is the metadata filtering. This actually helps in optimizing the rack performance. That is why we have covered it today. All these details are covered with 5 scenarios, which we have covered in this coding example, so that you can understand it in a better way. So first we import the ChromaDB and instantiate the client pointing local folder. This line basically will create ChromaDB in the same folder where your project is located. At each run, as we mentioned, there would not be any overwrite and vector created ones will survive the second run if you're restarting the laptop or restarting your machine. Next, we create the collection. You can think collection as a namespace, a way to create different set of vectors separate from each other within the same database. So if you have used the pine cone, you would know this as an index. So remember, if the collection already exists, say because you may have run the program multiple times, so it returns the existing collections, else it creates a new collection with that name. Also note, this just creates an empty container. Think of it like an empty folder, no index, no vector, nothing happening yet. HNSW index get built when we actually add the documents. But just another thing to note before proceeding to add documents to collection, note that the ChromaDB here defaults to L2 distance. But isn't we said cosine similarity is what captures the meaning of text? So why L2 distance? So just to explain, this is more of the historic thing. Early vector database used L2 and many just keep it as the default. For normalized vectors, it won't affect your ranking anyway. So both cosine similarity as well as L2 will give you the same ranking of the documents which are closest to the query vector. But if you look at the new vector database like Pinecone, cosine similarity is becoming more common default for the text search. So finally here we are adding 6 documents to one collection. Remember, index is built at this stage. So here we have 3 lists: document, metadatas, and IDs. And they are linked purely by the position. So index 0 in documents, index 0 in metadata, and index 0 in IDs all belong to the same record. ChromaDB just zips them together internally, and that ID is the unique key. try to add the same ID twice and ChromaDB will reject it. And that's how you update to delete a specific document later on. So now quickly about metadata once more. Think of this as a filter layer. So suppose you have 10,000 vectors to search. Your metadata filter could possibly first bring them down to 500. And ChromaDB runs the HNSW similarity search across those 500 vectors only. So the filter cuts the search space before any vector comparison happens, giving LLM more contextual and cleaner chunks to produce the final output. So finally, now move to the example. Here we are just printing some lines for formatting, and here we are querying the collection and producing the top three results. So end result is the argument which we pass to the collection.query in order to get the three of the closest match. And we are finally printing the document along with its distance score as a pair. So zip, which is a built-in Python function, just help us to work with two lists at the same time, pairing up the items at the same position. Now in the next example, so here in this example, we have applied the metadata filter as you see it here. So only documents where year is 2024 or later are considered. So point to notice filtering happen first and then semantic search runs within that narrow subset, improving both the speed as well as the relevance. And in the output, we are printing the metadata alongside the document and distance so that we can see exactly which records are matched. In the next example, we have used the metadata on the string field. So instead of year, we have used the topic. If you see here, it is matching those documents where topic is equal to the database, and we are again retrieving the top three results, and then finally printing the document along with its distance. In the next query, where here we have used the where document. So where document performs the filter on the content of the document. Think of it like an SQL like keyword, right? So supported operators are contains as well as not contain. So as you see here, we are trying to retrieve those documents which contains the word LLM. So again, the filtering will happens first, and then it will semantically search the closest documents, and we are printing the result. Finally, in this query, we are doing the combined metadata as well as the document filter. Similar thing, but we use both the where clause and where document clause, right? And then we are retrieving the closest three match and finally printing them. So I hope you can now see how the ChromaDB works, how to store documents with metadata, run similarity search, and apply filters to control exactly what gets retrieved. So now let's quickly run this example and see how it works. We'll go to the terminal. So we finally get the result. You see here for the query one, which is just based on the text, we are getting the three result. In the second query, which we applied the metadata filter on year, we are getting the three results along with the distance score. And the third query is about we are filtering based on the topic. We are getting the three results along with the distance score. And the fourth one, where we are querying because there's just one document, even we have applied the n result as 3, we are trying to retrieve 3, but just because only one document contains the word LLM, so it has retrieved just the one result. And finally the combined one, here also it returns the one result. So guys, this is all about this video. I hope the ChromaDB and semantic search much more clear to you right now. In the next session, we will dive into the files and explore index types in details like flat, IVF4, HNSW, which will give you much deeper understanding what is happening under the hood of tools like ChromaDB. And a few sessions after that, we will bring all together and build a full rack chatbot. As always, please come back with your questions and suggestions and see you in the next session. Thank you very much.